Welcome to Catalyst Medhub, where we ignite understanding and make learning easier. In our today's class, under carbohydrate chemistry, we shall be discussing on carbohydrate isomerism. Isomerism is just a phenomenon whereby two compounds have the same molecular formula but different structural formula. On that note, isomerism, they are generally classified into two. One, there is structural isomerism, and two, there is geometric isomerism. Now, the structural isomerism is the form of isomerism in which two molecules, which are the isomers, they have the same molecular formula but differ in the structures. Whereby the geometric isomerism is a phenomenon whereby two molecules have the same molecular formula, same structural formula, but they differ in the orientation of the carbon atom in a space. That is, they have different spatial arrangements. Carbohydrates, they are able to exhibit isomerism due to the presence of asymmetric carbon atom. Asymmetric carbon atom is just the carbon atom that is bounded by four different groups. For example, this carbon here is an asymmetric carbon atom because it's bounded by four different groups. Any carbon that is bounded by four different groups is an asymmetric carbon atom, and it is due to the presence of asymmetric carbon atom that carbohydrates are able to undergo isomerism. The number of the possible isomers in which a molecule can have depend on the number of the asymmetric carbon atom that molecule have, and the possible isomer can be calculated using the formula 2 raised to the power of n, where n is equal to the number of the asymmetric carbon that molecule contains. For example, if we take glucose as an example, glucose is hexose with 6 carbon, 1, 2, 3, 4, 5, 6. So here we'll be having OH, H, OH, OH and CH2 OH. This is the structure of glucose. This is the structure of glucose. If we are to count the asymmetric carbon here now, if you look at this carbon number 1 here, this carbon number 1 here is not asymmetric carbon because it does not have four different groups that is attached to it. If we expand it, the carbon number 1 here is this is the structure of carbon number 1, CHO. Same double bond O with hydrogen, then the bond that is attaching it to another carbon. Here, since it does not have four different groups that are attached to it, this carbon number 1 is not an asymmetric carbon. Now let's come to carbon number 2. The carbon number 2 is then with another C attached to it again. We can see that this carbon number 2 is asymmetric carbon atom because the group that is attached to it from the up is different from the group that's attached to it from the right side, is different from the group that's attached to it from the left side, and is different from the group that's attached to it from the below. So the carbon number 2 here is asymmetric. So starting counting number of the asymmetric, this is asymmetric 1. Then let's look at carbon number 3. This is carbon number 3. We'll be having this is carbon number 3 with another carbon 4 here. Now if you look at the carbon number 3 here, carbon number 3 here is also asymmetric carbon because the group that's attached to it from the up, down, right and the left, they differs. It has four different groups attached to it. So carbon number 2 here is also, carbon number 3 here is asymmetric. This is second asymmetric that we have in the structure of glucose. Now let's look at the fourth carbon. This is the fourth carbon, OH and H with 5th carbon here. Also, this fourth carbon is asymmetric because if you look at the structure that is attached to it from the up, down, right and left, they differ. It also has four different groups that is attached to it. So the fourth carbon is also asymmetric. Now the 5th carbon, this is the 5th carbon. This 5th carbon is also asymmetric because the structure that has to it up the same because it is similar to carbon number 1, 2 and 3. It has four different groups attached to it. So this is our fourth asymmetric carbon atom. To the 6th carbon, this is the structure of the 6th carbon is something like this. We are having CH2OH, C with 2 hydrogen and OH. We can see that this carbon here is not asymmetric because it has 2, because it does not have 4 different atoms that is attached to it. You can see from here now, hydrogen is the same thing. So it does not have 4 different groups that is attached to it. Since you are having hydrogens are the same thing attached to it. So from here, glucose has 4 asymmetric carbon atoms. 4 asymmetric carbon atoms. And we say that for you to know the possible isomers of the molecule, you raise the number, you raise the 2 to the power of the number of the asymmetric carbon atom. So from here, for the glucose, 2 raised to the power of 4 will be having 16. Meaning glucose have 16 different isomers. Again, if you look at the structure of fructose has 3 asymmetric carbon atoms. 3 asymmetric carbon atoms. So the possible isomer of the fructose will be 2 raised to the power of 3, which will be 8. So this is how you will know the number of the isomer that a molecule is likely to have. On a nutshell, we say that the carbohydrate, you are able to exhibit isomerism due to the presence of asymmetric carbon atoms. The type of isomerism that occur in the carbohydrate includes 1. There is epimerism. 2. There is D and L isomers. 3. There is anomerism. And 4, there is alpha and beta isomers. These are the common isomers of carbohydrate. First one, we say we have epimerism. Molecules that undergo epimerism, they are referred to as epimers. Likewise, the molecules that undergo isomerism, they are called isomers. So for the epimerism, the molecule that undergo epimerism is called epimers. And epimerism is just a phenomenon whereby 2 molecules, they differ from one another at only 1 carbon due to the difference in the orientation of OH group. That is, if the orientation of the OH group differ at only 1 carbon between the 2 molecules, they are referred to as epimers. Example, and epimers are usually derived in respect to glucose. For example, galactose and mannose, they are epimers of glucose at carbon 4 and carbon 2 respectively. Now let's draw the structure of glucose. 2, 3, 4, 5, 6. This is the structure of glucose. And we say that the epimers, they are those 2 molecules that differ from each other at 1 carbon atom due to the difference in the orientation of the OH. And we said galactose and mannose, they are epimers of glucose at carbon 4 and carbon 2 respectively. So here should be the galactose, and left here should be the mannose. Now, we say galactose is an epimer of glucose at carbon number 4. If we label the carbon here now, this is carbon 1, carbon 2, carbon 3, and carbon 4. So the galactose will only differ from glucose at carbon number 4, orientation of the OH at carbon 4. So now let's draw the structure of galactose. 1, 2, 3, 4, 5, 6. Carbon 2 is the same thing. Carbon 3 is the same thing as glucose. Whereby in carbon 4, there is difference in the orientation. In carbon 4 here, the OH of glucose is facing right. So for the galactose, it will be facing left. It will be facing left, whereby the hydrogen will be facing right. And carbon 5 is the same thing. So the difference in the orientation of OH at 1 carbon atom is epimerism. We can see from here, this is carbon number 4, and 1, 2, 3, 4, 4, 5, 6, and the carbon number 4 of galactose. For the glucose, the OH is facing the right, while for the galactose, the OH is facing the left. So galactose is an epimer of glucose at carbon 4. Likewise, mannose is an epimer of glucose at carbon 2. So now let's draw the structure of mannose. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. We say that mannose differ from glucose at carbon 2. This is the carbon 2 of the glucose. The OH is directed towards right. So here now for the mannose, the OH will change its position to the left, while the hydrogen will be to the right. Then any other carbon is the same thing as that of glucose. So we are having H, OH, OH. So this is the structure of mannose, which differ from the glucose only due to the orientation of the OH at carbon number 2. So mannose is an epimer of glucose, galactose is an epimer of glucose at carbon number 4. That is about epimerism. The next one is L and D form. L and D form. There are two molecules that differs due to the orientation of OH at the peritoneum asymmetric carbon atom. That is asymmetric carbon, which is second to the last carbon. So if the OH is oriented to the right, that is D form. But if the OH is oriented to the left, that is L form. So now let's take the structure of glucose as example. 1, 2, 3, 4, 5, 6. OH, H, OH, then CH2, OH. Here is hydrogen, HO, H. Then let's draw another one again. CHO, 1, 2, 3, 4, 5, 6. OH, H, H, 1, 2, 3, 4, 5, 6. Okay. H, OH, here is H, HO, and H. Now, we say that L and D form, they only differ at the peritoneum carbon asymmetric carbon atom. That is, the asymmetric carbon atom that is far away from the carbonyl functional group. If you look at here now, the carbonyl functional, the asymmetric carbon that we have is 1, 2, 3, 4. So this fourth asymmetric carbon atom is one that is farthest away from the carbonyl functional group, and those are the one that give reference to L and D form. We say that if the OH is oriented to the right, that is D form, but if the OH is oriented to the left, that is L form. Now, if we orient our OH to the right, this D glucose, this one will give us D glucose. But if you orient our OH to the left, like this one, this L glucose. So L and D form, they only differ due to the orientation of the OH at the asymmetric carbon atom, which is farthest away from the carbonyl functional group. If the OH is oriented to the right, it will give you D isomer, but if it's oriented to the left, it will give you L isomer. That is on L and D form. The next one is Anomerism. Anomerism. Two molecules that undergo anomerism, they are called anomers. But in this case, anomerism or the anomers, they are derived from the cyclic structures of the molecules. Now, in the cyclic structure, that is when the linear form of the molecule is converted to the linear form, there will be the formation of additional asymmetric carbon atom. The orientation of OH on this additional asymmetric carbon atom is what will give us anomers. And under the anomers, we are having alpha anomer or beta anomer. If the OH is on the same side with the CH2OH group or the hydrogen methyl group, that will be beta anomer. But if the OH is on the opposite side of CH2OH group, that is alpha anomer. Another thing again is that in the alpha anomers, the OH is downward, while by in the beta anomers, the OH is upward. Let's take glucose as an example. This one, then another one. Now, this is now our asymmetric, this is the new asymmetric carbon that is formed. This carbon here is our asymmetric, the new asymmetric carbon that is formed. So now, here we are having CH2OH, CH2OH, OH and H, OH, H and H. Also here we'll be having H, OH and H. Here we'll be having H, OH. Now, the only difference between this one and this one will now be the orientation of the OH at this newly formed asymmetric carbon atom. If the OH is upward, OH and H is down, and if the OH is downward. Now, if the OH is on the same side with CH2OH, that is beta anomer. And if the OH is on the opposite side of CH2OH, that is alpha anomer. In another time again, you can say that beta anomers, they are the anomers that have OH oriented upward, while by the alpha anomer, they are the anomers that have OH oriented downward. So this is about the anomerism. We should also know that there is what we call mutar rotation. Mutar rotation is the interconversion of alpha anomer to beta anomer, or from beta anomer to alpha anomer. That is mutar rotation. For example, alpha glucose can be converted to beta glucose. Likewise, beta glucose can be converted to alpha glucose. Their interconversion is called mutar rotation. The last isomers under carbohydrate is alpha and beta isomers. Again, now for these alpha and beta isomers, they are also called optical isomers. These ones, they are also called optical isomers. Here, they have the same molecular formula, the same structural formula, but they rotate a plane polarized light differently. The isomer that rotates a plane polarized light to the right is alpha or D isomer, whereby the one that rotates the plane polarized light to the left is beta or L isomer. So here they have the same molecular formula, same structural formula, but they only differ in rotating the plane polarized light. The isomer that rotates the plane polarized light to the right is alpha or D isomer, while the one that rotates the plane polarized light to the left is beta or L isomer. Now, any solution that contains equal amount of alpha and beta isomer, it is called racemic mixture. It is called racemic mixture. Racemic mixture is just a mixture that contains equal amount of alpha and beta, and they are electrically neutral because the activity of one will cancel out the activity of the other. This is about the carbohydrate isomerism. Kindly subscribe, like, comment and share. Don't forget to turn on your notification bell so that you don't miss any new video.